Hi, welcome to Module 15, Tolerancing. In this module, we're going to learn what's the purpose of doing the tolerancing. And we're going to also discuss the type of the tolerance, how you represent it in a different way. We're going to use a shaft and hole assembly to give you some examples and tell you some of the terminology about the tolerance. There are two different kind of unit system, and each one of them using a little bit different way. We're going to show you an example, and you're going to practice how to look at the table to find out the tolerance. And the last, we're going to discuss the tolerance accumulation. The material of this topic is related to these standards, the ASME, ANSI. You can find more detailed information from the textbook. If you are using the new edition 2018 and later, it's going to be in chapter 13 and 14. 2016 will be in chapter 8 and chapter 9. One is about the theory of the tolerancing, and the other one is how you can use tolerance in AutoCAD. So what is the purpose of doing a tolerancing? Well, the main reason is we wanted to be able to do an interchangeability. And what does that mean? If you manufacture a part, especially in our industry, all the parts will be mass production. And if you wanted to have a replacement, you certainly wanted to make sure that the replacement part can fit into your device. So we wanted to be able to interchangeable part, and in order to do that, then you have to make sure the size will fit. But there's no way that you can make size all be the same. So we make a tolerancing, meaning in certain range, then the device will be able to interchangeable. Now, what is the feature on an interchangeable part dimension? Well, you look at this example. If the exact dimension is simply 1 inches, but it's not possible it's going to be always to be 1 inches. So we make a range of the values, and that range of the value is allowed us to have some buffer to be able to interchange parts in that range, and it will always be able to find a part that fits. A tolerancing is the amount of the size of a variation permitted. So there's certain terminology you have to be careful. When we talk about the tolerancing, it simply is the range of the value. So if you have a size and you set a limit, an upper limit and lower limit, where the upper is 1.005, lower is 0.994, then the tolerancing is the difference of these two values. That's how we define the tolerance. So why do we want a part size to be controlled by two limits? Well, it is necessary because it's impossible that we can mix things exactly the same. And that's the reason that we need to have this kind of variation. But if you can make the tolerancing to be small, that means you can have a very good quality control to make the variation of the size to be minimum. But it doesn't come for free. It comes with a cost. To make things to be more exact or smaller tolerance, you have to pay a cost to control the manufacturing process. So that's the cost, and that's the trade-off. And when you design a thing, then you have to think about the purpose of your project or your product. Do you need a very precise tolerance, like very small tolerance, to get the more precise dimension, or you allow this variation to be larger? If you allow the variation to be larger and which is not critical, then you might be able to save a lot of money. So that is the reason that you should pay attention to when you design. You have to pay attention what kind of tolerance you are going to use. Now, choose a correct tolerance for a particular application depends on several things. Now, we just mentioned the first thing is the purpose, the function, the intended function that you want it to be. And then second is the cost. As we mentioned, more of smaller of the tolerance, meaning the more of the cost. And also, if you wanted to make it very precise, sometimes you have to use some very special manufacturing process, and that will be costly as well. And the last thing will be the experience. People in the industry knows when you have this kind of purpose, and then you should set a limit in that range. As you can see in the later part of this module, we're going to give you an example, and there's like a standard table, and that table is based on the experience and is well recognized by the international community. What are the type of the tolerance? Well, we can represent the tolerance by several different ways. The first way is called the limit dimension. The second is you can use plus minus and with a tolerance, which is a value between the upper and lower limit. You can also use a page or block tolerance, meaning you're going to put a note to represent the tolerance for overall. So let's show you some examples. Let's look at the limit dimension. So limits are the maximum and minimum size of a part. So usually you represent that by putting these two values in parallel, one on the top and one at the bottom. You can also write it as in sequence with a dash. So that's two different ways that you can represent it. And you can also use the plus minus. If you use plus minus, then when you put a plus, then the later value, meaning you can go over to the first value, which is the actual value that you desired. And the second bottom value will be the minimum value. That will be the smaller than the standard size value. So this standard size, we also have a terminology called the basic size. And remember, this is called the basic size because we are going to use this terminology in the future table. Now, the third way, as I mentioned, you can also mark the tolerance in a like a whole way. You can put it in a block, just like in the title block. Usually in the title block, you're going to have a section, and you can say, unless otherwise specified, all such and such is going to be in the tolerance of such. So depends on the decimal point you're going to use. If you see the dot cross, and meaning if you have a value which is 0.57, then the tolerance will be plus minus 0.01 inches. And that's how we use a general node to represent it. So here we give you an example. If you have this general nodes, and then you have a dimension which is equal to 1.501, and you look at these has 3 decimal point, which is this one, then the tolerance will be in this case, which means the upper value will be this value plus 0.005, and lower value will be minus 0.005, and that's the value or the range of the value should be. Let's look at the shaft and hole assembly. This is the most common place that you have to think about the tolerance. So the majority of the example we're going to show you is to look at how a shaft and a hole is going to fit. If you look at the picture here, you notice that on the left of the shaft we give like 2 different diameters. the big one and the smaller one. On the right hand side, the hole also have two different dimensions, a big one and a smaller one. When you have the smaller one, meaning it's the minimum range, this is the minimum value of the diameter, and the capital D represent the maximum diameter. Both the shaft and the hole could have two different variation number because of the tolerance. So how do we see this, and how do we manufacture parts? It's critical. If the shaft is too big, then you might not be able to fit into a hole. And if the hole is too tight, then the shaft will not be able to fit into the hole. So let's define several terms before we go into the tolerancing. And we're going to start with the inch. So when you have the inch, remember the whole number represent a millimeter, which is matrix. And in inches, we use two digits after the decimal point. First, we look at the limit. So the limit meaning which you have a maximum and minimum size that you can allow the parts to be. So that means you have two values. One is the upper limit and the other one is the lower limit. The basic size, as we mentioned previously, is the desired dimension that you wish to attain. And the variation will be based on the basic size. Tolerance is the difference of those two values. So is the value that you permitted to vary. Let's work on an exercise over here. Here we have a shaft, we have a hole, and we want to fit these two parts together. You look at the shaft, then we mark the diameter to be 0.51 and 0.47. This kind of dimension is what we call the limit dimension. So limits, we have two different limits over here, and one is 0.51, one is 0.47. The whole dimension is over here, which is 0.50 and 0.49. And what will be the basic size? If you look at these numbers, you probably can guess the basic size is actually going to be 0.50. The limits that we have, if the shaft is 0.47 to 0.51, then the hole should be 0.49 to 0.50. And basic size should be 0.50. What about the tolerance? The tolerance is the difference of the upper and lower value. So you subtract these two values, you're going to get these two, which will represent the tolerance. So these are the basic terminology that you should know. Now we have more terminology and which are important for our specification of the tolerance. One is called the maximum material condition, the MMC. The MMC is the size of the parts when it consists of the most material. What does that mean, the most material? Which means if you have a shaft, the shaft contains the maximum material, meaning the size of the shaft is the largest. However, the hole, if you have a larger size of hole, that means you have a smaller amount of the material. So for the hole, the material, the maximum, the MMC should be at a condition where the hole size is the minimum. Let's use this example to explain the MMC and LMC. Previously, we defined the MMC. The LMC is totally opposite to the MMC. So MMC, you have the maximum material. LMC, you have the least amount of the material. As we mentioned, if you want to have the maximum material for the shaft, you're going to use the largest size. And the hole, you're going to use the smaller size. So the shaft, you should use the 0.51. The hole, you should use the 0.49. Well, LMC, you're going to use the shaft to be the smaller one, which is 0.47, and the hole you're going to use the larger size, which is 0.50. And that's the meaning of the MMC and LMC. And based on that, we can also define what is the maximum clearance and what is the minimum clearance. The maximum clearance meaning the distance between the shaft and the hole is the maximum. And that actually can be calculated by the LMC of the hole and also the LMC of the shaft. The LMC represents the minimum, the least amount of the material condition. Now, when you do the minimum, and that this also known as the allowance meaning the minimum clearance. If you're smaller than that, then it will not fit naturally. And that is defined by the MMC of the hole minus the MMC of the shaft. Let's look at this example to do the calculation. We want to find out the maximum clearance and the minimum clearance. Remember, the minimum clearance is also known as the allowance. So what is the maximum clearance? The maximum clearance is the maximum of the shaft and the maximum of the hole. And look at this one. What is the LMC for the shaft and LMC for the hole, and also the MMC for each one of them? You should be able to identify for the shaft, LMC is the least amount of material, should be the smaller diameter, which is 0.47. And for the hole, it's going to be 0.50. So you subtract these two values, you will get the maximum clearance for the condition. So if you make the shaft to be smaller and you make the hole to be larger, then that will give you the maximum clearance. If you don't remember what we said previously, then just use this idea to get what is the maximum clearance. If you have the minimum clearance, meaning the largest of the shaft and the smaller of the hole. So largest of the shaft is 0.51 and smaller of the hole is actually is going to be 0.51 and 0.49. So the difference will be minus 0.02. All right, so what does a negative clearance means, right? So when we follow that formula and use those values to do the calculation, we get a negative value. What does that mean when you have a negative clearance? Well, you look at the size of the shaft, it's 0.51. The hole is 0.49, meaning the shaft is larger than the hole. If you wanted to fit, meaning you have to force it to fit. So we have several different kind of fit, and the type of the fit can be categorized into a clearance fit, interference fit, transition fit, and line fit. There is a video that you can watch after this video. So I encourage you to watch that video to understand what are the difference of the fit. Now let's just explain some of the condition. Let's start with the clearance fit. If you have a clearance fit, that means it's always a space. So there's no interference. That means your minimum clearance, which is allowance, should be greater than 0. Interference fit meaning you are going to have a condition that possible you're going to have an interference between parts. It's either equal to 1 or it's less than 1, meaning the allowance is going to be negative. So there's no space that allow you to fit your shaft into a hole. And it also have another terminology called transition fit. When you have a transition fit, then it depends on the size of the shaft and the hole, and there could be a space or no space, meaning the variation of the value could allow you to have a clearance or not. There's some possibility when you set the allowance, the tolerance of parts which you are not possible to have any of the clearance, and that will be what we call the interference. And the last one is what we call the line fit. So when you have a line fit, meaning there is a space or could be there is a contact. When you have a contact, meaning the size of the hole and the size of the shaft is going to be equal. So this is opposite to the interference. When we have an interference, is going to be less or equal to 0. Now here we have a greater than 0 and or equal to 0 condition. Now these are important because when you watch the later part of this video, we're going to show you an example. You have to use a table and you have to identify what kind of a fit that we are using. So let's think about this in the real life. What are the possible things that we will use these two different terminology? Why do we have a clearance? Why do we have an interference? And what is the purpose of that? For clearance, meaning you absolutely going to have a space. So these are the example. You have a lock and key. You don't want to have an interference. Otherwise, the key will never ever be able to fit into the lock, or it's very hard for you to fit that into the lock. And coin slide, if you play those like a slot machine, you certainly want the coin to be smoothly slide into the machine. But sometimes we need to have interference, right? If you have a hinge pin and you want that to fit into and it's not get loose, so sometimes that if you play those like a Lego, they also will make interference because you don't want to have a loose parts that will come out naturally. So, and that's why you want to have an interference. The interference give you the friction in between parts, so the parts will not fall out easily. All right, think about this problem, and your exam will probably have a question similar to this. So I want you to think about this exercise and go back to the book and practice this before we give you the answer. Let's look at this problem. Pause if you need it. Write down your answer, then you compare your answer with our solution. Okay, let's look at this problem. The first one set that you have a shaft limit and hole limit. And you look at these two set of number, what will be the basic size? Well, the basic size normally is not going to be some very weird number such as 1.1072. It's going to be some nominal size that we usually use, either like a whole number or by a quarter or even by 1/8 of the number. So this case is obvious the basic size will be 0.5. And then you look at the variation of two things. What kind of fit would that be? If you look at a shaft, the shaft is always going to be smaller than the size of the hole, which means you're going to have a clearance, right? It's always going to have a clearance that you can fit the shaft into the hole. The second one, very obvious, this should be like 3/4, 0.75. Now, what about the type of a fit? Do you guarantee there's always clearance? Well, no. If you have a shaft that is 0.751 and a hole to be 0.75, there's going to be an interference. So what happens if you have that situation, that you could have a clearance and you might not have the clearance? Well, that's what we call the interference. Let's look at the third one. 0.373, 0.378, etc., etc. That should be 1/8, which is 0.375. Then you think about, would you be able to have a clearance or not? Well, it looks like you could, but the value you could have will be fall into the transition case. Go back and look at the case of the transition to find out how we define the transition. I'll let you look at the textbook by yourself so you will understand how you can determine which case that is. And obviously the last one we wanted to test you is going to be the condition of line. And the basic size will be like a quarter, that 0.25. So look at this table and make sure that you understand the different type of the fit just based on the limits of the value. Now, we're going to discuss an AMSI standard limits and fits. AMSI is an organization that set these limits. In your textbook, at the end of the textbook, there's an appendix that you can find several different tables. We're going to show you how to use those tables. And they give you a different acronym, and those acronyms represent different kind of fit. Now, we're not going to cover in detail to distinguish what kind of fit that is. Our purpose is to teach you how to use those tables. Now, RC represent one kind of a fit. LC, LT, LN represent another kind of fit. FN also represent another kind of fit. If you look at the terms of the definition of that, the FN, for example, is the force fit. That means you have to force it in order to fit it. That means there's interference always. So it doesn't matter which one that is. If the problem gives you what kind of fit that is, then you have to go to the corresponding table. For example, if we give you the RC fit, then you have to look at the table A-A.1.1. Let's do an exercise and have your book with you so you can exercise this by yourself with us. We're giving you a basic size of 0.50 inches, and we want a fit called RC8. Okay, remember these two are the most important information: basic size and the type of the fit. This is a RC fit. It's a running clearance fit. And you have to look at the Appendix A. Now in the Appendix A, there's two different unit systems. One is for inches and the other one is for metrics. The way to distinguish is actually by looking at the acronym they give you. So the RC is based on the inches. The other type of the fitness of the fitting is based on what we call the H and G, and those kind of a fit is called the matrix limit and fits, and that's in your Appendix A.2. The A.1 are the tables for the inches. A.2 are the tables for the metrics. This is the table A.1.1 in your textbook. Now, as we mentioned, we have a basic size 0.5. We have a fit, which is RC8. And the way to look at that is just look at the coordinate. You have a row, you have a column. The column represents the kind of a fit, where we have a kind of fit is RCA, so it's going to be in this row, this column here. And then you look at the basic size. So the basic size is on the rows, and it's 0.5. So you look at here, they give you the range of the basic size, and 0.5 is right at here. So this two numbers give you the location what you should use for your limits. So the standard limit for the hole and the shaft is defined by the row and the column, and this one is the one that you should use for your purpose. So the 2.80 is for the hole, and minus 3.5 minus 5.1 is for the shaft. And you write down these two values and remember what your basic size is. Your basic size is 0.50, and if you look at the hole, that will be plus 2.8 and 0, and the other one will be minus 3.5 and minus 5.1. But wait a minute, if you think about this value, what is the basic size? The basic size is 0.50, and you are adding this value. Is it reasonable? You have 0.50 and you add these 2.8. That's quite a bit of value that you allow it to vary, right? So if you look at the table carefully, you actually is not going to add that value directly. If you look at the top of each one of the table, they will say the limits are in thousandths of an inch. So when you see this value you have to divide by 1,000. That is the actual value you're going to add or subtract. Okay, so the table tells you it's in the thousand of the inches. You have to divide the value by 1,000, and these are the actual value that you should use for the limit. Okay, so this value we already divide by 1,000, and that's the value that you should use. Let's look at another example, and more example is on the back of your textbook. You are also going to do a lab, and which will practice your understanding about this torrance table. Here we show an actual object that you have a milling jack assembly, and with several different parts. As you can see that some of the parts has to fit into the other. And how do we use this one to show the torrance and be able to dimension that on your drawing? Here is an assembly view. As you can see, the several different parts. The basic size they give you is 0.375, which is 3/8. We want to determine the limits for both the parts. And what both parts? We're looking at the V anvil here. So this one will fit into the kernel, the nut. So how do we find those? Well, the basic size is given is 0.375, and RC4 is the limits for the fits. So you look at the table. When you look at the table, and you will be able to find the limit information. But when you do the dimension, you can dimension that by dimension the basic size and also the type of the fit. But if you want to dimension the limit, then we should need to find the limit based on the previous example. just by looking at the basic size as the row and the type of the fit to be the RC or other kind of like FN, using those two to specify what it should be add or subtract. And remember, those number has to divide by 1,000. So if you look at the table, I'm not going to show you the table, but try to look at the table, see if you can come up with this value, which is the correct value for the shaft. Sorry, this is for the hole. And on the right hand side is for the shaft. Okay, verify this result on yourself and to kind of prove that you understand how to use this. If you don't, go back to see the example and watch it carefully and understand the procedure and use this one to verify your understanding. All right, if we wanted to mark another part, which in this case we're looking at the sliding screw. Where is the sliding screw? Is this one here. And this will be the screw, and this one actually the base is going to have a hole. This will be like a shaft. This one will be a hole. And I give you the basic size is 5/8, and RC5 is the type of finish. Again, open your textbook, look at the appendix 8.1, find which one give you RC5, and look at the row which is 0.625 to be the basic size, and then you find the vertical one represent RC5. Then you should see the value for the limits. And again, you have to divide by 1,000. So based on that, then you can find the value for the shaft to be 0.62731, 0.6238. Same thing for the hole, and then you can find these two values.